Hello, this is Miss Goodwin, and today we are covering Objective 4.1, Right Triangle Trigonometry. So the objective is that we can solve for missing measurements in right triangles using trigonometry with the Pythagorean theorem. Now today we are only focusing on the sides. Angles will be in another video. Let's go ahead and get started with the sides of a right triangle. So there are three sides to any triangles, and when we have right triangles, we have special names for them. These names are dependent on where the reference angle is located. The reference angle is just one of the two acute angles in either corner of the triangle, not the right angle over here. So reference angle will be given to you, at least its location. Now there are three sides to this triangle. The first one is the hypotenuse, and that is going to be the longest side of the right triangle. So the longest side, it is also across from the right angle. And that is this side right here that I'm highlighting in green. Our next side is the adjacent side. That is the side that is touching our reference angle here. So the side that is touching the reference angle, that is not the hypotenuse, is the adjacent side. Our last side is this opposite side right here. It is across from the reference angle. So the reference angle is right here, going across, that gives us our opposite. And again, these sides are dependent on where our reference angle is. So I've gone ahead and colored the reference angle purple on the left side, and I will do that again here. This is our reference angle. Both of these triangles are in the same orientation, but the reference angle is going to be the top right one instead this time. Hypotenuse is still the longest side. Adjacent is still touching the reference angle, so it's going to be the right side this time. And our opposite is going to be across from the reference angle. So notice that even though the triangles are in the same orientation, the hypotenuse is still that longest side. That's not going to change. But if our reference angle switches, then the opposite and adjacent are going to switch places. So that's it for the sides so far. Now we're going to switch over to the Pythagorean theorem, the next section on the notes. So the Pythagorean theorem is used to find a missing side when you are given two sides. So if we are looking for a side and we have two sides, we can use the Pythagorean theorem, which is this formula right here. A squared plus b squared equals c squared. Now, in reference to the side names we just learned, we can also say it's the opposite, side squared plus the adjacent side squared plus or equals the hypotenuse squared. So the hypotenuse is by itself in the Pythagorean theorem. So these are the three sides of a right triangle. And we're not always going to be given the angle, but we can still use this Pythagorean theorem. to find one of the sides if we're given two others. So let's look at an example, two examples. The first one is going to be if we're looking for our hypotenuse C, which is this side right here. That is our C. The other two sides are A and B. It could be either or, especially since we don't know the angles. But the C has to be that hypotenuse. So let's go ahead and set this up. We get A squared plus B squared equals C squared. A is going to be 20. So 20 squared plus B, which is 14. 14 squared equals C squared. We don't know what C is. That is what we're looking for. So now we just solve. So 20 squared is going to give us 400 plus 14 squared, that is 196. And that is still equal to C squared. 400 plus 196 is 596. That is still equal to C squared. Now we want to take the square root of both sides to get rid of this 2. And the square root of 596 is 24.4. And that is what C is equal to. You are done with that. So that's what it would look like if you're solving for the C, the hypotenuse. Let's look at another example where you're looking for one of the other sides. So this time we have C. We are looking for either A or B. And again, it doesn't really matter which one you label A and which you label as B. I'm just going to keep it consistent, but you could do either or. So our formula is still A squared plus B squared equals C squared. A is 5, so we get 5 squared plus B squared, we don't know what B is, equals 17 squared. That gives us 25 plus B squared equals 289. Now, our goal is to get the B alone. We want that alone. So we have to get rid of the 25, and we could do that by subtracting it. What you do to one side, you do to the other. That leaves you with B squared equals 264. Now from here, you take the square root of both sides. That gives us B equals 16.2. And we are done. So just be careful, make sure you're plugging in your numbers right, and then subtract if you're moving over the equal sign. That is the Pythagorean theorem. Now we have to look at trigonometric ratios. So we are going to use these when we are given at least one side and one angle, one acute angle. The reason it has to be acute is because we've been dealing with right triangles, so they're always going to have a 90-degree angle. But you need to know what the value of the acute angle is and of at least one side before you can use your trigonometric ratios. So I've gone ahead and filled in our three sides according to this reference angle here. And we have the three functions, sine, cosine, and tangent. You may recognize these if you did the vocab assignment on Tuesday. We're going to use two sides for each of these ratios. So sine of your reference angle, we're going to call that angle theta, which is what this symbol is right here. Sine of our angle is the opposite divided by the hypotenuse. Cosine of our angle is the adjacent divided by the hypotenuse. And last but not least, tangent of our angle is equal to the opposite over the adjacent side. So divided by the adjacent. A little mnemonic or acronym you can use is SOHCAHTOA. So we have sine is equal to the opposite over the hypotenuse for so. CAH, is saying cosine is the adjacent over the hypotenuse. And lastly, TOA is for tangent, being the opposite over the adjacent. SOHCAHTOA. Now, what do each of these pieces mean? Because there's a lot of information given in each ratio. So the sine, or if you have cosine or tangent, that is just the trig function that we're using, or trigonometry function. It's like a machine that you throw your reference angle into to get a number, a fraction, a decimal. The reference angle is denoted by this little guy we call theta. And that is just a variable. We call that specific one theta. It is Greek, so you could say you're learning Greek now. And then, as we know, sine is the opposite over the hypotenuse. But cosine is the adjacent over the hypotenuse, and tangent is opposite over adjacent. These are just the lengths of the sides. Whichever ones you're using. So however long that side is, that is the number that goes there. So these are our trigonometric ratios. Let's practice a bit on the next page. On the printed copy, just a heads up, on the printed copy, I forgot to mark the angles, so make sure you get those in your notes. But let's go ahead and practice this. Our first step is to always label the sides. So I know with this top triangle, my opposite is right over here. My adjacent is down here. And my hypotenuse is right here. We know sine is opposite over hypotenuse. Opposite is 10, so that will go in our numerator. And our hypotenuse is 15, so that will go in our denominator. So our fraction is 10 over 15, which is 2 over 3. Let's do that again with cosine. Cosine, we know, is the adjacent over the hypotenuse. So the adjacent is 5. And the hypotenuse is still 15. So we get 5 over 15 for our fraction, which is 1 over 3 when simplified. Our last function is tangent. That is the opposite over the adjacent. So we get our opposite of 10 over our adjacent, which is 5. 10 over 5 is just equal to 2. So that's it. We're just dividing the two numbers for our ratios. Now let's look if we have variables. We're going to start by labeling our sides as so right here. And then let's start with our functions. So sine of theta is the opposite over the hypotenuse. Opposite is t. And no, I lied. Opposite is z. Hope you caught me slacking there. And our hypotenuse is v. Cosine of our angle is the adjacent over the hypotenuse. Adjacent is t. And cosine is still, or hypotenuse is still v. Last but not least, we have tangent, which is the opposite over the adjacent. Opposite is z. Adjacent is t. So that's what your ratios look like. Now, remember how I said earlier we use these with one angle on one side? Let's go ahead and practice that now. So you can use trig ratios to find sides when you're given at least one side and a reference angle. If you have that reference angle on one side, you can use this. You can even use this instead of the Pythagorean theorem even if you have both sides. So our first step for doing this is to identify sides and given information. So we are given our reference angle of 43 degrees. Our opposite is over here, and that is x. Our adjacent side is right here, and that is 6. And we're not given anything else, so that is all the information we have and or are looking for. So now we need to pick from SOHCAHTOA the sine, cosine, and tangent. Since we have our adjacent and we're looking for our opposite, we are going to use the tangent, because tangent of our reference angle is the opposite over the adjacent. Hello, hello. So let's set up our function. We're going to do tangent of our angle, which is 43 degrees. That is equal to the opposite, which is x, divided by the adjacent, which is 6. So we have tangent of 43 degrees equals x over 6. Now, if this scares you, you can plug that straight into a calculator. That will give you 0.933 equals x over 6. And I'm going to show you how it would look both ways if you choose to multiply it now or not. I said multiply, I mean plug in tan of 43. Either way, we're going to start by multiplying both sides by 6. So just like any other algebra problem, our goal is to get that x alone. So we have to multiply both sides by 6 to cancel that out. Now here, that will leave you with 6 times tangent 43 equals x, which is the same as 6 times 0.933 equals x. And then you just multiply this in your calculator, which gives you x equals 5.6. So x equals 5.6. No matter which way you did that, if you did the tangent 43 first or at the end, either works. But that is your final answer. Let's look at one last example. And once again, we are going to start by labeling what information we have. So we have our reference angle, of course. That is going to be 40 degrees. We have our opposite, which is 3.19. And we are looking for our hypotenuse, which is x. So now we have to pick from SOHCAHTOA. We have the opposite. We're looking for the hypotenuse. That means we're going to use SO, or sine. So sine of our angle equals opposite over hypotenuse. And then we're going to solve it again. Plug in your information. So we get sine of 40 equals the opposite of 3.19 over our hypotenuse of x. If that sign scares you, you are welcome to plug that into a calculator right now to get 0.643. I like to use 3 digits for this part. Okay. So now there are a few more steps because the x is in the bottom this time. But it's just one more step actually. So first, we're going to multiply both sides by x. And this cancels out the x on the right-hand side, leaving us with x times sine of 40 equals 3.19. And on the left side, that gives us x times 0.643 equals 3.19. Now to get x alone, we divide by our sine of 40. And I hope you have more space than I do. And you'll do that on both sides of the equal sign. And on the right hand side, if you took care of that sine 40, that's just 0.643. That cancels that out, that cancels that out. So you get x equals whatever this is. And that is 4.96. So x equals 4.96, no matter which way you do it. And that's it. That is how you find the missing side of a right triangle. You could use that, you could use the Pythagorean theorem if you're given two sides. But you are done. Go ahead, write a summary now, and get started on the practice. Have a wonderful day. Bye!